Good morning. Today, I'd like to continue with the topic that we had just barely mentioned in the previous video. This has to do with infinite series. In particular, I want to hit 4 points today. Firstly, I want to talk about geometric series. These are certain types of infinite series that are particularly nice to deal with. After that, we're going to think of a general infinite series, and there'll be some good news associated with that. Unfortunately, there'll be some closely related bad news as well, and then, combining the good with the bad, there will be some weird news to go along with it. I'm going to form a new sequence of numbers. I'll call these numbers capital S. The S is for sums. S number 0 will just be the A number. S number 1 will be the A number plus R times the A number. S number 2 will be A plus A times R plus R times A times R, which is A times R squared, and so on and so forth. If the A number is 0, all of these partial sums are 0, and it's not going to be an interesting thing to look at. So I'm going to assume that the A is not 0 here. This collection of numbers, S0, S1, S2, and so on, either converges to something or it doesn't converge to a thing. We want to investigate what happens if we allow the number of terms to become indefinitely big. Thinking of some number k, a plus ar, so on and so forth, until you get to the term that has a times r to the k in it. This is an ordinary algebra style sum of a finite number of terms. All of the things that we know from algebra apply to this sort of thing. So if I say that I want to calculate r times some number k, I'm simply going to take each one of these terms and multiply it by r before I add them together. A times r, ar times r is ar squared. The very last one will be r times a times r to the k power, the a times r to the k plus 1 power, and the term immediately before that will have a power on the r that is 1 less than k plus 1. That is to say, the term will be a times r to the k power. Once again, both of these sums are ordinary finite terms, college algebra type sums, so I don't feel the least bit bad about doing algebra on them. I'm going to calculate S number k minus r times S number k. I'll write that down on one side of an equation, and I want to think about what's going to happen to the rest of it. I'm going to subtract this from that. The a times r term cancels out. I'm going to subtract that from that. The a times r squared term cancels out. I am going to subtract away a times r to the k from this. That term cancels out as well. Out of all of these terms written down in these two sums, when I subtract, the only thing that doesn't go away is that term. And since in the first sum there is no a times r to the k plus 1 power, this term will stay around as well. For the moment, I'm going to assume that r is not equal to 1. We can look into the situation where it is as a separate case shortly. If r is not 1, 1 minus r is not 0, and it's okay to divide both sides of this equation by the number 1 minus r. So what we've done here is we've actually found a formula for partial sum number k. A plus AR out to A times R to the K power is exactly equal to that number minus that number. In this first number, there is no reference to K. In this number, there is a factor that has no reference to K and a part that does have the reference to K in it. I want to think about what happens to these sk numbers as k tends to infinity. This r number, if r is less than 1 in absolute value, then these numbers are going to be increasingly large powers of things that are less than 1 in absolute value. R to the k plus 1 will tend to 0 in that case. On the other hand, if absolute r is bigger than 1, these numbers will become indefinitely large and not settle down to anything. So, allowing the index on the partial sums to become indefinitely large, if the r number has absolute value less than 1, then this limit exists and is actually equal to that number minus 0, a over 1 minus r. If absolute r is bigger than 1, then this limit doesn't exist, it diverges, and the situation where absolute r is exactly equal to 1, we will deal with separately. This is actually kind of strange because if I think of all of the different numbers I'm adding up, there's a times r, a times r squared. There is an unlimited supply of these numbers, an actual honest-to-goodness infinite number of them. But if a certain condition holds, then I can add up this infinite collection of numbers and get, contrary to what you might think, a nice finite number out of it. Let's look at some examples of this kind of thing. A specific example of this kind of infinite series, known as a geometric series, is this: 3 plus 3 times 2/3 plus 3 times 2/3 squared, and so on and so forth. This is a series of type geometric where the a is equal to 3 and the r is equal to 2/3. Because 2/3 has absolute value less than 1, what we have figured out is that this infinite series converges. As I add more and more terms on, the partial sums begin to look more and more like a certain particular number, which we can actually calculate. If you add up a very large number of these terms, the sums are going to begin looking more and more like 9 as you allow the number of terms to become indefinitely big. If I have this infinite series, which if you prefer you can write in this form, this is also one of these geometric series. This time the a is equal to 4 and the r is equal to -1/7. the absolute value of r is 1/7, which is less than 1, this infinite series converges to something. We know sort of generically in this situation that the infinite series converges to a over 1 minus r. Simplifying the arithmetic, it turns out that this infinite series has value 7/2, 3.5 if you prefer decimal. Previously, we stated that the case where a is 0 is not interesting enough to look at. So I'm going to assume that a isn't 0. The only case for the r number that we haven't thought about is when the absolute value of r is 1. That can happen in one of two different ways. R could be 1, or r could be -1. So we will now investigate those two special cases separately. Let's think about partial sum number k. That'll be a plus a times r, a times 1, plus a times r squared, all the way out to a times r to the k power. The r, of course, being 1, means that all of the powers of r are equal to 1 as well, counting 1, 2, out to k, and then there would be that one, k plus 1. I am adding up k plus 1 copies of the non-zero number a. If you take the limit as k becomes indefinitely big, this factor is a constant that is not 0. These are numbers that are becoming indefinitely big. The limit of the SKs can't converge. So if r is 1, a geometric series must diverge. If you look at the similar case where r is -1, the partial sums begin with a, then a plus a times r works out to be 0. A plus a times r plus a times r squared will be equal to 0 plus a times 1, a. The next one after that will be 0. These numbers never settle down to anything. They oscillate back and forth between a and 0. So once again, this kind of geometric series diverges as well, but the way in which it diverges is different. The first one had partial sums that became indefinitely large in size. This one doesn't do that. This one has the partial sums alternating back and forth between two fixed values. In either case, though, the partial sums don't settle down to some particular single number, so you have to say that the partial sums diverge. If you have a geometric series, the term that has the r to the n in it is a times r to the n power. If the geometric series converges, that's when absolute r is less than 1. In that case, these a times r to the n power terms must tend to 0. This makes you think maybe that's a more general thing. It makes you wonder, if you have an infinite series that you know converges to some actual real number that I will call s, is it true that the limit as n tends to infinity of an must be 0? The fact that the infinite series converges to s means every partial sum with a big enough index must look a lot like s, with the looking alike becoming better as the index gets bigger. S number n minus 1 is a number 1 plus a number 2 out to a number n minus 1. I am no longer thinking specifically of geometric series. I'm just thinking of an infinite series. By making the index large enough, this can be made as close to S as you care to make it. The thing is, though, that that's also true of any other partial sum. So I'll pick the n big enough so that S n minus 1 looks an awful lot like S. The next partial sum must look even more so. If I subtract partial sum number n minus partial sum number n minus 1, these are just ordinary algebra sums. The thing about the relationship between them is every term that appears here as well, and I have the additional a sub n. Partial sum number n minus partial sum number n minus 1 is actually equal to a number n. As it stands right now, there's no arguing with this. It's just ordinary algebra. I have to be extremely careful about what I do next, though, because there's a subtle point. This is a sum that has a finite number of terms in it. So is that. When I subtract them, I end up with a number n. As you allow the n to become very big, whatever these numbers do is the same as what those numbers do, but I don't know on the face of it yet that the limit of those things even exists. I have to be very careful about this. So for a moment, I'm not even going to think about this. I'm going to think about that. I have to ask myself and remember properties of limits. When is it legal to break a limit of a difference of two things up into the limit of the first thing minus the limit of the second thing? It is not universally okay to do that. The only time you're guaranteed that that's okay to do is when both limits exist. From our discussion, the limit of these quantities is the number S, so the limit of those exists. The limit of these numbers, as n tends to infinity, exists and is also that number, capital S. It's legal, firstly, to split this up into the difference of the limits. The premise, though, was that the infinite series we're talking about converges to some number S. This limit is S, that limit is also S, and S minus S is 0. Having carefully figured this out, I now go back and say, look, the limit of those numbers is 0, but those numbers are the a sub n's. I want to summarize this very carefully. I want to say exactly what I mean and not say something other than that. If an infinite series converges, then the limit of its individual terms must be 0. If you gave me an infinite series and I looked at its individual terms and they didn't go to 0, that would tell me that certainly the infinite series in question does not converge. That's the logical contrapositive of this statement. Let's look at another one of these. I want to look at the sum n equal 1 to infinity of 1 over n, the individual terms, 1 over 1, 1 over 2, 1 over 3, and so on, do tend to 0 as n tends to infinity. So the series must converge, right? Pick a positive integer, positive whole number, k, and I'm going to add some stuff up. I'm going to take 1 over k plus 1 over k plus 1 plus 1 over k plus 2. I'm going to keep adding until I get to 1 over k plus k, 1 over 2k, and then I'm going to stop. That's a nice finite algebra sum, so all of my usual algebra ideas work. I have two thoughts that I want to think about here. How many terms are there? If I start counting using that 1, there'll be 1, 2, out to k, and then there's that one. There are k plus 1 things that I'm adding up. Out of all of these k plus 1 terms, if you think specifically, for instance, of maybe the k is equal to 4, you would have 1 over 4 plus 1 over 5 plus 1 over 6 plus 1 over 7 plus 1 over 8. The smallest term is the one down at the end. I'm going to add up k plus 1 things, each of which is at least as big as 1 over 2 times k. So this sum that I'm looking at, it's at least as big as k plus 1 times 1 over 2k. On the other hand, k plus 1 is bigger than k is. Taking that fact into consideration, 1 over k plus out to 1 over 2k is at least as big as 1/2 is. Now, this is a strange little side calculation, which at first glance doesn't seem to have anything to do with what we've been talking about, but it turns out that it does. It turns out that this is sort of the kiss of death for that infinite series that we're talking about. Obviously, 1 over 1 plus 1 over 2 is bigger than 1/2. That's seemingly a silly thing to say, but then 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6, this number is at least 1/2, and so is that. If I add up to the 1 over 6 term, the result is at least as big as 1/2 plus 1/2. 1 over 1 out to 1 over 6. The next term will be 1 over 7. Just keep going until you get to 1 over 2 times 7. This is at least 1/2. That's at least 1/2. That's at least 1/2. So if I start at 1 over 1 and keep adding until I get to 1 over 14, that sum is at least 1/2 plus 1/2 plus 1/2, and so on, and so forth. By adding up a finite number of terms, I can make the partial sum bigger than 1/2, bigger than 1, bigger than 1.5, bigger than 2. If I were willing to continue writing these things down, I can make these partial sums as big as I want to make them. The partial sums do not settle down to some actual real number. One could write the infinite series equals plus infinity, but I want to emphasize here this infinite series does not converge to anything, it diverges. If you're thinking back to what we were talking about a bit ago, though, you're thinking, hold on, wait a minute here. In the series we're thinking of, the individual terms go to zero. Doesn't that mean that the series converges?
Right? Wrong.
In the thinking that we've done so far, do we have a sentence that says, if the individual terms tend to zero, then the series converges? Our bag of tricks for infinite series right now is very small. Really, the only new thing we know is that fact. So the answer to my question is no, we don't have any such sentence. If you give me an infinite series that you know to converge, then I guarantee you its individual terms tend to zero. But this example shows me that there are infinite series whose individual terms tend to zero, which do not converge. So we're going to have to be very careful about our language now. This is the bad news. I have to warn you, what I'm about to write down is wrong, as we'll see in a minute. So here's what we do. I want to look at the sum n equal 1 to infinity, 1 over n minus 1 over n plus 2. Obviously, there can never be any difficulty, and you can obviously write this as the sum n equal 1 to infinity, 1 over n, minus the sum n equal 1 to infinity, 1 over n plus 2. Now, we already know from our preceding work that that first sum equals plus infinity. This is terrible notation, and people should be ashamed of themselves. What about that infinite series? The first term in it would be 1 over 1 plus 2. It would be 1/3. If I look at a later partial sum for this, this partial sum will be at least 1/2. The next term would be 1 over 7. Keep going until you get to 1 over 14. That'll be at least 1/2 plus 1/2, and so on and so forth. This infinite series also equals plus infinity. The snarl in my voice was intended to convey disgust. Then presumably infinity minus infinity would be 0. So the infinite series converges and is equal to 0. Except this is completely wrong. The error is this. The infinite sum is a limit of ordinary sums. When is it legal to split a limit of a difference of two things into the difference of the limits? When both of them exist, and despite the equal infinity thing, neither one of those limits exist. This calculation is illegitimate. That doesn't mean the infinite series converges all by itself. That's yet to be determined. Instead of trying to deal with the infinite sum, I'm going to look at a partial sum. I'm going to look at S number k, which is the sum n equal 1 to not infinity, but some particular positive whole number of these things. all of a sudden college algebra is back on the table because I'm only adding up a finite number of things. In this sum, the first term is 1 over 1, then you'll add 1 over 2, 1 over 3. The last one that you will add will be 1 over k. In this sum, the bottom of the fraction is n plus 2, not just n. So this is going to begin when n is equal to 1 with 1 over 3. Then there'll be 1 over 4, 1 over 5, 1 over 6, and when n is equal to k, the last term will be 1 over k plus 2. The thing I want to notice is there are going to be some terms in common between these two things and some terms that are not in common. I'm going to write out enough terms explicitly so that we can clearly see what's in common and what's not. In the second sum, the last term is 1 over k plus 2. The term before that is 1 over k plus 1. The term before that is 1 over k, and I can clearly see that the 1/3 are going to cancel out. The 1/4 will as well, all the way out to the 1 over k terms. The things that don't cancel out are the 1 over 1 plus 1 over 2 terms, and minus 1 over k plus 1 minus 1 over k plus 2. Once again, there's only a finite number of terms that I have to deal with. As k tends to infinity, s number k is going to approach 3/2 minus 0 minus 0. So the infinite series does converge to something, and it's 3/2. If we were sloppy in our thinking, we would work directly with this, try to split it up into two infinite series, and then subtract what they converge to. But unfortunately, that worked out to be infinity minus infinity, so that clearly was not the way to go. What does work is we look at a partial sum, do a little bit of algebra, get a formula for the partial sum, and then take the limit as the k index tends to infinity. In this particular case, 3/2 was the value of this infinite series. As we go along, we're going to have to be very careful about our thought processes. I can't always split a sum of a difference of two things up into the difference of the sums, because these infinite sums are limits of things, which are tricky. Coming up next, we're going to talk very briefly about a certain type of integral, and then develop an idea that under certain circumstances will give a yes/no answer to, does an infinite series converge? In the meantime, I hope everybody has a good day. I'll talk to you again soon.